All right. Howdy, everyone. Excuse me. So, today's class is going to be pretty much the same as the last lecture that we had on Thursday, where I'm just going to give you a traditional lecture and then we're going to call it a day. Hopefully, I'm hoping that Thursday will be in person, and if Thursday is in person, we will be doing an activity. We will first sort out the group situation. And then you will all break into groups and do an activity of my making, and hopefully it will not go to astray. Excuse me, just sinuses. Yeah. So with that being said, let's get started. So last time we asked a very fundamental question of what is an exoplanet. Today, we're going to be asking the fundamental question of how do exoplanets, planets form in the first place? How did the Earth come into existence? How did Jupiter come into existence? How did hot Jupiters come into existence? So forth and so on. Well, in one of the ways to answer that question is through a process known as comparative planetology. So effectively, in general, the way it works is theory must be anchored by observation. Either the theory comes into place and then you find the observations later, like with general relativity. General relativity made certain predictions which were then observed to be in the universe, or you can make a set of observations and then apply a theory to it, such as how Newton applied the theory of gravitation to the already accepted or already observed motions of the planets. So, comparative planetology comes into this in that it supplies the basic observations that need to be accounted for in terms of any sort of fundamental formation theory or any sort of fundamental mechanism by which the planets would form. Right now, we have effectively a data set of one. Granted, with the additional thousands of planets that we're finding, that data set is going to expand rather quickly, rather largely. And well, I would say that we have a complete data set of a stellar system of one. We have information on other stellar systems, but that information is very incomplete. So when we look at so we're going to be using our solar system as a blueprint for how the solar system got created, and then apply the observations of the exoplanets to alter that theory so that the existence or the observations of those exoplanets can be accounted for, can be explained. So when we look at the solar system can be broken into effectively two constituent parts, that being the sun and the eight planets that are surrounding it. Again, I'm not going to belabor my definition of planet, but the astronomical consensus, we have the sun, which is roughly the center of the solar system, and then surrounding it, you have eight major bodies: Mercury, Venus, Earth, Mars, Jupiter, Saturn, and Neptune. Last time I talked about the definition of planet, just to refresh your memory. The accepted definition is a body that orbits a star, is massive enough or rather, created around a star, is massive enough to be under its own gravity to be a spherical shape, and has cleared its orbital neighborhood. Uh, Now, if we wanted to take a more complete inventory of the solar system, there are a lot of other bodies in the solar system that are of smaller size, but are in fact actually, generally speaking, far more numerous than the planets. While if you look at in terms of mass, the planets still dominate. But if you took a look at it in terms of number, the planets are actually a rarity within our own solar system. And that inventory includes things like comets, meteors, sorry, comets, asteroids, meteoroids, things known as trans-Newtonian objects, and dwarf planets, and so forth. So, or TNOs, as we call it. And so I'm going to go over each of these briefly, and each of the characteristics of each of these objects is important to the overall theory. So when we talk about the characteristics, we're talking about where are these located? What are they made of? What do their orbits look like? That sort of thing. And again, the reason why we're interested is this becomes the foundation, these sets of observations become the foundation for any theory or any overarching framework that is used to explain the creation and evolution of said planetary systems, because we do believe that from our observations, we've known that planetary systems can evolve or change significantly over time. For instance, there is speculation that, well, not speculation, we have fairly strong evidence that the current positions of the planets are not what they were not what they were when they formed. Jupiter and Saturn were somewhat closer together, and they were somewhat closer to the sun. There is some speculation that Neptune was actually interior to Uranus at one point, and then got kicked out to a higher orbit. So planetary systems can change over time, and so acquiring as much information about these systems in specific and in general is going to help inform us of how these things came into being and how they evolved. When we look at the solar system, we can now define it in effectively four rough regions. That is the region occupied by the terrestrial planets. Then you have the asteroid belt, which distinguishes or seems to be a demarcation between the terrestrial planets and the Jovian planets. The Jovian planets are both the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. And then beyond that, we have another region called the Kuiper Belt. Um, the asteroid belt is mainly comprised of asteroids, as the name would imply. The Kuiper Belt is mainly comprised of cometary material and trans-Newtonian objects and dwarf planets and so forth. They are not exclusively, some of those are not exclusively located in the Kuiper Belt, but essentially that's the uh, basic population. The other thing I should note about each of these regions is that they are roughly planar in orientation, meaning that we define a plane in the solar system called the ecliptic. That plane is the orbital plane of the Earth going around the sun. When you look at the orbits of the planets, the inclination of those orbits relative to that ecliptic is not very large. It doesn't exceed 10, 11%, or 10 or 11 degrees. Not quite as narrow, but still constrained, are the asteroid belt and Kuiper belt. Both of these also are somewhat disc shaped in that most of the objects in the belt are located near the ecliptic, whereas you see few of them um, above and below, same with the Kuiper belt. So when we look at the size of the solar system, we zoom outward. There's another structure which is theoretical. We actually do not have direct observations of this structure. We have inferred its existence based on what we call long period comets, comets that have periods that are 100 years or longer. Uh, we believe because of the the eccentricity of the orbit, plotting the orbits out, we can determine their semi-major axis, and we can figure out how far away they can get. And given the trajectories of these, we effectively have theorized that there must be a cloud of cometary bodies that are in a spherical distribution around the solar system, around the inner solar system, the Kuiper belt inwards. And that cloud is known as the Oort cloud. Again, these have never been observed directly at those locations simply because they are very faint objects. Well, they don't really produce light in and upon themselves. They have a little bit of heat, but not much. And they are small, they're far away, and they do not reflect sunlight very well or very easily. If you're interested in watching, I'm not going to play it in this class, but if you're interested in watching, I think a very well produced and very well thought out scale model of the solar system, I would highly recommend finding this YouTube video. The link should be embedded into the YouTube or into the PowerPoint slides, which I will then post to Canvas if I haven't already done so. It's about 8 minutes long, and effectively a group of young individuals went out to a desert in Nevada, and they created a scale model based on the size of the sun. Um, can't remember what the size of the sun they use. I think they just arbitrarily said, all right, if we have a sun that's a meter in diameter, what does the rest of the solar system look like in comparison? So basically we know what the diameter of the sun is. It's around 600 and around 700,000 kilometers. Um, we know what that diameter is, and they scaled it down to 1 meter. So what does the rest of the solar system look like? And they found that Neptune would actually be around 21 kilometers. I think it's 21 kilometers away. Really, really far. And so, like I said, very well produced, very interesting video. They also have one on scaling time, which I think is even more just uh, awe-inspiring to see just how the time scale of the universe, particularly humanity's length within that time scale, um, is for me it was very moving. Watching that was very moving. But anyway, let's look into the properties of the 8 planets. Well, uh, the next 3 slides are going to be talking about, things like relative size, composition, orbital distance, rotation direction, and other things. So let me summarize all of those. I don't want to read them to you, but let me summarize effectively the highlights of those. And then you can refer back to those tables at a later date if you want to look at very specific things. First thing that's pretty obvious is that all 8 planets are spheres or roughly spherical in shape. All 8 planets, as I just mentioned, orbit around the sun in a relative flat plane, what we call the ecliptic. There is a little bit of variability, or variation, but it's basically a plane. They all revolve around the sun in the same direction, meaning that if you look down onto the solar system from the north, basically, if you went from the north geographic pole of the Earth and went way up so that you could see the entire solar system, you would notice that the planets revolve in a counterclockwise direction. All of them do. All of the planets rotate around an axis of rotation, meaning that, they experience a day-night cycle. All of them do. Now, and most of them, 6 of the 8, their rotation is also counterclockwise. So they are moving like this as they move around like that. So counterclockwise seems to be the preferred direction, if there is any, in the solar system. The two major exceptions to this are Venus and Uranus. Venus actually has almost a complete retrograde rotation, meaning that it rotates clockwise. If you assume that counterclockwise is the correct orientation or the initial orientation, its north pole is now south and so it's if this is 0 degrees tilt, then Venus has a axial tilt of around 98 degrees, if memory serves. Uranus has a intermediate tilt to that, so not nearly as extreme. Its axial tilt is roughly speaking around, um, I'm sorry, it's around 180. Yeah, 180. Uranus has an axial tilt of around 92. So Uranus, in a sense, is rolling through the solar system. Why do these planets have differing axial tilts to the rest of the solar system? That's still somewhat of an open question, particularly for Uranus. For Venus, the leading hypothesis right now is that a large impact caused it to flip over. Some kind of planetesimal very early on, or some very large body early on in the solar system smacked into Venus and caused it to flip on its head, essentially. When we look at those regions before, they're just the regions seem to be demarcated by the asteroid belt and the Kuiper belt. But if you look at those regions specifically, if you look at the terrestrial planets, these planets all have reasonably the same density of about 5.5 grams per cubic centimeter, which indicates that the body is primarily made up, or on average, has the same density as magnesium silicate. And so I mean, we'll talk about later that these planets are actually have iron, nickel, and a whole bunch of lighter elements in it. But on average, these four interior planets uh, have densities of around 5.5. Mercury is a little bit weird; its density is a little higher, but again, which we also kind of attribute to an impact. And then Mars is actually a little bit less dense, but again, on the whole, what this tells us is that the terrestrial planets are primarily composed of rock, solid or semi-fluid rock. The four outer planets, the gas giants and the ice giants, are not. Their densities are very similar to one. In fact, Saturn's density is slightly less than one. So if you had a large enough bathtub, Saturn would float. Uranus and Neptune are a little bit more dense than Jupiter and Saturn are, but again, relatively close to a density of 1 gram per cubic centimeter, which means those planets have to be primarily composed of gas, as the names would imply. Uh, Ice giants simply indicates that there are more ices, frozen elements in the upper atmospheres in these planets than with Jupiter and Saturn, but they are also primarily composed of hydrogen helium gas, very similar in composition to the sun. Another trend that we see within the solar system is that for terrestrial planets don't have moons, uh, pretty much. So for instance, the moon Earth Moon system is unique and probably it's unique within our own solar system, but it might in fact be very rare in other stellar systems. Effectively, we believe that the moon was created through a process of, you guessed it, a collision. A body that was hypothesized to be around the mass and size of Mars, slammed into a primordial Earth at an oblique angle or a shallow angle, and then broke off some of that material, and all of that kind of broke into pieces and then coalesced into a disk surrounding the Earth. And then from that disk, the moon then formed. So it was by, I hate to say random chance, but it is by basically by chance that the moon formed. It is not expected to be a natural process. So Mercury doesn't have a natural moon. Venus doesn't have a natural moon. Mars, what I mean by natural moon, is a moon that formed with it. Mars does not either. Mars does have two moons technically. They are Phobos and Deimos, but they are potato moons, and effectively they are captured asteroids. These bodies presumably formed somewhere near or at the asteroid belt, and due to gravitational interactions, they got sent into the inner part of the solar system. They traveled too close to Mars, and Mars's gravity well captured them. One of the two, and I can't remember which one, actually has an orbit that's degrading. Eventually, over the course of, I think it's on hundreds of thousands of years, it's eventually going to actually hit Mars. It's actually going to deorbit entirely. But my point here is that the expectation is that if a terrestrial planet forms, it's not going to have a moon. On the other hand, with the gas giants, with Jupiter through Uranus, all of them have moons. All of them have major moons. All of them have moons that we believe formed with the planet themselves or very shortly after the planet was formed. Now, you might see numbers like with Jupiter and Saturn that they have 90 plus moons or 100 plus moons. When I was coming up, the competition, the number that seemed to change almost monthly was the number of moons around Jupiter and Saturn. The vast majority of these moons are captured asteroids. They are small, rocky, irregular shaped objects that, again, probably originated in or about the asteroid belt and astronomic or gravitationally got kicked outward and then got captured by Jupiter, or were in the very early stages that were just whizzing around all of the solar system, which I'll explain in a moment. They got captured then. So not formed in the vicinity of these planets, but captured. But there are moons that were formed in the vicinity. So our expectation is if we find a gaseous planet somewhere else, then it's a natural or a good assumption to say that those planets also have moons that formed around them. Again, if we do not see this, that would be very interesting in that, again, as I said last time, it would seem to indicate that our solar system is unique in some way or very weird in some way. The other things that are common among all of the gas giants but are not found around terrestrial planets are ring systems. Now you're all familiar, hopefully you're all familiar with the ring system around Saturn. You have this very flat plane of material that encircles Saturn like a record, As it happens, all the other three also have ring systems. They're not as noticeable. In fact, Neptune's was only seen when Voyager passed behind it. They are very tenuous. In fact, one of the great mysteries of the solar system is why Saturn still has a ring system that robust. Um, we would expect these ring systems to dissipate over time. Essentially, that material would either get blasted out or fall into the planets themselves. So, what is keeping Saturn's disk system so large and for such a long period of time is still something of a uh, is an active question or an active research question at the moment. All the gas giants have rings. None of the terrestrial planets have rings. Magnetic fields. The magnetic fields of the gas giants are large. Magnetic fields, relatively speaking, of the terrestrial planets are either non-existent or very small. The and also the magnetic fields of the terrestrial planets, if they exist, are roughly speaking in line with the axis of rotation. So the north magnetic pole is not too far away from the north geographic pole. For Jupiter and Saturn, they're pretty much dead on. The axes of rotation are aligned. For Uranus and Neptune, they are no way aligned. They are very much tilted, and in Uranus's cases, the center of the magnetic field is actually off center to the planet. Again, we don't really understand why. But any formation mechanism has to account for the fact that gas giants seem to have very high magnetic fields, whereas terrestrial planets don't. What else can I say? Um, asteroids. Asteroids in the asteroid belt, pretty much rocky bodies. They're composed of either silicates, carbon, or iron and nickel. They are most almost asteroids by definition are irregular in shape. They have roughly sphere. Oh, the other thing I mentioned, forgot to mention, planets have a nearly circular orbit. Their orbits are almost perfect circles. Not quite, but almost. Same goes with the asteroid belt. There is more the range of eccentricities or the range of non-circularity, if you will, is larger than you find in the planets, but it's still basically a circle. The inclination is also basically constrained. Kuiper belt is a more extreme version of the asteroid in terms of the motions of things. It's composed of irregular bodies that while we suspect that these bodies do in fact have heavier elements in them, they are primarily composed of ices, water ice or methane ice or what have you. Their orbits are also roughly circular, but the range is larger. They are also roughly constrained to the plane of the ecliptic, but that range again is larger in comparison to the rest of the solar system. So, I think I've gone through all that. So yeah, and there are a couple other things, but effectively, those are the main highlights. Um, Asteroids, comets, meteoroids, and trans-Newtonian objects. Oh my. These are um, somewhat dismissively referred to by most astronomers as solar system debris, which will be clearer when I talk about how we believe the solar system formed. These are again smaller bodies. They're irregular in shape. There are a few circular ones or spherical ones, but these are objects that just seem to um, just proliferate the or exist in large numbers within the solar system. But again, and their orbits are much more chaotic in range. Now, if we compare asteroids to comets, asteroids typically are anywhere between are found to be. This is a little misleading because I talked before about something known as a selection effect, something known that a we see a range of, say, a range of masses, in this case, sizes. And so when I say that asteroids are roughly between 1 to 1,000 kilometers, the 1,000 kilometers you can basically take to the bank. We do not, asteroids typically do not get any larger than 1,000 kilometers in diameter. Um, The reason for that is if they were larger, based on the density of the material, they'd actually form spheres. They'd actually become or be dwarf planets. Now, the smaller end of the cycle, that's nah, that is less certain because that is not motivated physically. And bodies that are smaller than a meter are extremely hard to detect. And so there are probably millions, if not billions, of asteroids that are less than a meter, but we just can't observe them. So, roughly speaking, of the observable asteroids, they're roughly between 1 to 1,000 kilometers. Oh, sorry, not meters, 1,000 kilometers. Comets, on the other hand, again, we have this selection bias in that comets are even more difficult to observe. The best observations we have are really the comets that are actually coming into the inner solar system, like Hale-Bopp, Halley's Comet, Hyakutake, those sorts of things. And we believe that those comets are roughly around 100 meters to 50 kilometers in size. The 50 kilometers in size is not is again, you can pretty much take that to the bank. the selection bias is not going to affect it nearly as much as with the smaller bodies that are going to be harder to see. Asteroids, as I've said, are primarily composed of rock and metal, whereas comets are primarily composed of ices. Um, and I've talked about um, the other characters. Although, again, asteroids typically seem to have low eccentricity. They're circular in orbits. Their inclinations aren't higher. But the Kuiper Belt or comets um, can have very high eccentricities, particularly those that we believe stem from the Oort cloud. They have eccentricities that are, zero point 0.8, zero point 0.9. These are extremely elongated ellipses, and they are and can be fairly randomly distributed. Kuiper Belt, not so much, but Oort cloud, definitely. Um, Asteroids. Let's skip to let's skip to this graphic because I like pictures. Actually, no, I'm going to go to that one. So again, this illustrates these are images of the asteroids Hilda, Gaspra, and Ida. Planets are named after planets are named after deities. Craters are named after scientists. Um, but moons are generally speaking some mythological creature, and some demigods, things like that. Asteroids, no idea. I have no idea what why asteroids are called what they're called. Like what Ida is, I don't know. But you can see they vary in shape. They're irregular in shape. They can vary significantly in size. And what's also interesting about them is that they can have moons in a way. Ida, for example, has a very small object called Dactyl, which is orbiting around it. The very center or the center of orbit of these two bodies is actually within Ida. So Dactyl actually appears to revolve around it. So these can be fairly complex in their construction. The other thing that we know, or the other thing that we suspect and actually have evidence for now because of DART, um, so you're aware, our best defense against asteroids is to hit it in the head with a rock. So you may have heard of this thing called the DART mission, which I don't remember what the acronym stands for, but effectively, there was another binary system of two moons whose name escaped me at the moment. And we launched a satellite, which was primarily composed of tungsten, if I remember correctly. And we just slammed it into one of them. And we were looking to see how much of a deflection, how much of a change in the trajectory of the smaller body would result from smashing it in the head with a satellite. And it turns out that it matched prediction pretty well. But that prediction also is predicated on the idea that the asteroid is not like a solid rock, that the asteroid is actually at least partly is a conglomeration of a whole bunch of smaller rocks that are just sort of gravitationally associated with each other. That in fact, this not these aren't very good examples of it. These are probably solid rocks, but there are some asteroids that you can look at. You can look like they're very pebbly. They seem to be composed of a lot of smaller different rocks, and so we think that there are asteroids out there that are just kind of a whole bunch of smaller asteroids that sort of collide together gravitationally and have agreed to travel through the solar system together. And so we saw a whole bunch of we the deflection of the asteroid was not as much as one would expect if the asteroid were a chunk of rock. There was some amount of kind of cushion, as it were, loose material like gravel, that it slammed into first and then dissipated outward. Composition of asteroids. The classification of asteroids can get complicated. Um, but generally speaking, they fall into three rough categories: stonies, irons, and stony irons. Stonies are composed primarily of carbonates and silicates. Irons, as you might kind of infer, irons are composed of iron and metal. A friend of mine actually has an iron meteorite, and it is extremely deceptive because when you look at it, it's pretty hefty. I mean, it's pretty good size. Like how she got this thing or how much she paid for this thing, I don't know, but it probably wasn't cheap. It's good size, and it's on her table. But when you look at it, it's dark in color, and you might think, okay, this probably isn't that heavy. It's damn near impossible to not impossible to lift, but when you try to lift it, it's like trying to lift Thor's hammer. It is way heavier than it looks. So iron is extremely dense. So there are bodies that are almost entirely made up of iron and nickel that are floating out there. And then you have the stony irons are some combination of the two. Additionally, within the stonies, there is a subcategory, excuse me, of carbonaceous chondrites. These are asteroids that appear to have, or rather meteorites, that appear to have pebbles. Basically, it appears to be a rock that seems to be some kind of cementing of a whole bunch of pebbles together. And in those chondrules is carbon, a great deal of carbon material. Whereas in other rocks, it's basically just straight on through. It's just evenly, it's just a rock all the way through it. Asteroids in water. One of the active mysteries of our solar system is, why does the Earth have water? Now, you might think Earth is the only planet in the solar system, or really it's the only body in the solar system that has any sort of liquid water on its surface. Venus doesn't have it. Mercury certainly doesn't have it. And Mars, we believe, did have it, did have water, did exist on its surface, but no longer exists. And there are explanations for why that is the case for those three bodies. But for the Earth, where that water originally came from is still pretty hotly debated as to where it stemmed from. The general consensus is that most of it did not originate on the Earth. That the Earth, when it formed, and if you were to form it in kind of a vacuum with no other objects, you wouldn't really have a whole lot of water in it upon itself. Believe that the water was primarily transported by asteroids or comets. You have water frozen. Water will exist in the outer part of the solar system in a liquor in an ice state, and then it will the orbit of that object will bring it into the inner solar system, and it slams into the Earth, and it will deposit those water molecules onto the surface, which, depending on the temperature of the surface, will become either liquid water, a gas, or solid ice. Stay solid ice. Or yeah. Now, observations don't exactly match prediction, meaning that we have a pretty good idea of what the water looks like in our on the Earth. Water can change depending on effectively the isotopes of the elements. So you have H2O. So if you have, for example, instead of just a normal hydrogen atom, a deuterium atom, a different isotope, something that has a different or has a proton and a neutron stuck together in the nucleus. That technically is water. It's hard water, if again memory serves. Um, and so you can look at the ratio of hard water to uh, D2 D2O to H2O, and there's a certain average ratio of that on the planet Earth. You then look at comets and look at this that same ratio, and they don't really match. So we don't know if water was in fact deposited on the Earth. There has to be some mechanism, terrestrially, presumably, that changed the ratio of those two elements relative to each other. But that's generally the consensus. Asteroids are interesting for another reason, and we'll touch upon this later, is that, well, I hesitate to say asteroids. There is another sort of component to the solar system, and that is dust. There is the zodiacal dust. There is dust grains that are on orders of like microns, one millionth of a meter, and they are just pervasive throughout the solar system, and they lie, and a lot of it lies within the ecliptic range or ecliptic disk. What's interesting about that is, or notable about these pieces of dust, is that we believe that those pieces of dust actually uh, hold complex molecules on them. Sugars and possibly even amino acids are formed on those bits of dust. That they provide the lab table for which those elements can collect and actually merge into more complex, longer, more complex molecules. Most of the asteroids are located in the asteroid belt, but not certainly not all of them. There are these groupings. Here, they're both labeled as Trojan asteroids. Others have listed them as Trojans on one side, Greeks on the other, hence an allusion to the Trojan War. But these are objects that are located in a very specific location in the gravitational field of Jupiter and Saturn. They are known as Lagrange points. So if you look at the Sun Jupiter gravitational system, you find that if you look at the amount of gravity caused by both bodies, that there are certain points where they are sort of either wells, basically, or hills. What I mean by that is it's a location that, if it's a well, if you stick an asteroid in that location and then just leave it alone, it will stay in that location relative to Saturn and Jupiter over a long period of time. The hills are somewhat like that. If you put an object right in that location, then it will also stay, but it's much easier to perturb it. It's much easier to knock it out of place, and when you do, it goes off in some different direction. Basically leaves. It is no longer nicely constrained within the system. The Trojan asteroids are located in L4 and L5. They are in basically gravitational wells. And so, even if there's a little bit of gravitational interaction between themselves or possibly even Saturn, they don't generally tend to leave that location. So, those are the major groupings of asteroids. You also have what are known as near Earth asteroids, NEOs. And there's a few different subsections of those. So, we do have some asteroids that are of a high-ish population in the inner part of this solar system. We know where most of them are located. We know where 99.9% of them, I believe, or at least 99% of the ones that would truly wreck our day, that would basically would be planet killers. But that percentage gets depressingly lower as you get to smaller and smaller objects. And so that is something that astronomers are very keen on mapping out. We actually have telescope arrays that are designed specifically to find all of the asteroids, particularly the near Earth asteroids around the Earth, so that we know whether or not they're going to smash into us or not. Because if they are, our best solution at the moment is hitting the head with a rock, which, I'm not overly impressed with. Comets. Their comet is composed of three rough regions or components. You have the nucleus of the comet. That is the solid part of the comet, where that is the part of the comet that is the metals and the ices. Generally speaking, that's the thing that's roughly around 10 to 50 kilometers in size. Surrounding that is if the comet gets close enough. So if the cometary body, if this particular comet, for example, were way beyond Pluto, then it would probably just be the nucleus. As that nucleus comes closer to the sun, it's going to heat up. That's going to cause the ices on the nucleus to sublimate. Because the pressure is nearly non-existent, when you heat up water ice, for example, it doesn't go to a liquid, it immediately goes to a gaseous state. And that is known as sublimation. And so as the nucleus travels closer and closer to the sun, it warms up, the water ice sublimates, and other ices sublimate and form a kind of a cloud around the nucleus, which we call a coma. As it gets further and further in, it develops tails, which are basically the iconic thing about comets. Is when you think of a comet, you think of something like this, which is Hale-Bopp. You have a bright front, as it were, followed by this kind of tail or a streak of brownish material coming off of it. In fact, and so if you were to do naked eye observations, that's probably all you would see. It's just this brown tail that's coming off of it. In fact, there are actually two tails. The brown tail is called the dust tail, but there's also something called the ion tail, which is bluish, that is a straight line. Now, how are these tails created? As that comet gets closer, it sublimates those gases or sublimates those ices into gases. The dust that was effectively frozen in those ices now is free. It now escapes also off the nucleus and is hanging around the coma. And so you have solar winds. So the sun puts out a wind, meaning that it basically produces pressure outward via two mechanisms. One is literally light. Light exerts what is known as radiation pressure. Now, it is minute. Obviously, while we are experiencing it, like the light coming off this monitor is in fact causing some pressure on me. It is so minute as to be negligible. But in the deep space and in these regions of the solar system, radiation pressure, when you're talking about micron-sized bodies, can move them fairly significantly. And so this radiation pressure will push these cometary materials away from the nucleus. Basically, will slow the coma material, and that material will slow, and the rest of the comet will continue at the same speed, and will just kind of start outpacing it. The ion tail is a little different. The ion tail is when you release these gases, you're also releasing not just the dust, but also free electrons. So there are electrons that are not bound to any particular atom. We refer to those as free electrons. They're basically free to go wherever they want by themselves. The sun also produces a very massive magnetic field, and those electrons are sensitive to that magnetic field. And so those magnetic field lines coming off the sun can trap those electrons and push them outward. So the dust tail is, as the name would imply, composed of dust. The ion tail is composed of negatively or positively charged particles, either free electrons or atoms that have been stripped of electrons that have some kind of overall charge to them. If they have an overall charge, they are sensitive to the presence of magnetic field and can be moved away, can be pushed outward. The dust tail is primarily brownish in color, as you might expect from dust. And the interesting thing about it is that it is generally curved in shape. It's rarely just straight. You'll rarely find images of comets. Hello, cat. You'll rarely find images of comets where the dust tail is not curved in one way or another. You can almost think of the dust tail as where the comet has been. That is, this is a material that's trailing behind the comet. So when the comet is coming in, the dust tail is behind it. Um, well, no, shouldn't say that. Let me take that completely off the table. That is material that is being pushed out. So when the comet is coming in, that's the material is like where the comet has been in a way. But as it goes around the sun and goes away from the sun, the tail will flip around because that material is always being pushed outward away from the sun. The tail, in some cases, can actually precede the nucleus. The ion tail, and again, it's curved. The ion tail is almost entirely straight. It is basically just a radial line off of the comet that's pointing directly away from the sun. So if I were to have an image like this and you were to ask me where the sun was, and my cat is very much interested in the bluebirds that are in my tree, um, if you were to ask me where the sun was in this image, I could tell you that it is pretty much somewhere along a line that is um, bottom left or bottom left from this comet. Basically, because of the orientation of the ion tail, it's not to the left, it's not to the right, it's down and to the left for each of them. Comets can come from effectively two comets are classified in two rough ways: short period comets and long period comets. And the demarcation between the two of them is pretty arbitrary, basically a century. Um, in a way, short period comets are referred to that because there's a possibility that you could actually see it twice within your own lifetime. Halley's Comet, for example, has an orbital period of 76 years. Um, it last came into, I think it was in the mid 80s. So uh, I probably will not see it again, but y'all will probably see it again. Your kids might actually see it when it comes back around, depending on how long everybody lives. So again, short period comets are labeled as such because their orbital periods are less than 100 years. Hopefully I said that before. Not 100 days, 100 years. Um, but generally speaking, if a comet is going to have an orbital period of 100 years or less, that generally means that that comet originated in the Kuiper Belt. Now, long period comets, comets that have periods longer than 100 years, generally speaking, are believed to be coming out of the Oort cloud. Kepler's law basically tells us that the semi-major axis, the size of the orbit, is relative to the period of the orbit. It's a function of the size of the orbit cubed is equal to the period of the orbit squared, approximately. Um, so, and we'll return to that later when we talk about detection methods of exoplanets. So if you have a comet that has a long period, that means that it has a larger orbit. And so therefore, It has to come from further away. And again, long period comets also tend to be far more elliptical than short period comets. Ooh, there's a pretty robin. Sorry, ADHD. Squirrel. Um, so yeah, so they are roughly speaking separated into short and long period comets, and they roughly align with where they came from. I've talked about this one in a little bit before in terms of where does we believe that asteroids and comets are probably the source of where the water stems from the Earth. Incidentally, we think the Earth is covered by 70% water, 70, roughly 70% water. But in comparison to the entire body, the ocean water is actually a very thin veneer. If you were to look at the amount of water in percentage to the entire planet, the Earth is a desert. It's very arid. It doesn't have a lot of water to it if you look at the planet in total. Whereas Europa, Enceladus, these moons of Jupiter, they are primarily made of water and ice. And we believe that there are planets, exoplanets, that have similar compositions to them. So, where did the little, comparatively speaking, where did the small amount of water come from on um, on the Earth? And again, we think that's from comets and asteroids. Meteoroids. Oh, oh wow, there's a robin right there. Meteoroids. Now, these objects, for reasons I still have yet to investigate, are odd in the way that they're named. The same object has three different names depending on where it's located. So if that object is located beyond the Earth, floating in the solar system somewhere, it's called a meteoroid. If it's within the Earth's atmosphere, if it is a shooting star, that is known as a meteor. If it's on the ground, it's known as a meteorite. And I have no idea why. I have no idea why its location causes its name to change. Meteoroids have compositions that are very similar to asteroids. One really can think of meteoroids as being the asteroids, but just on the smallest range. So meteoroids typically have sizes from 1 meter down to grains of sand. These are known as micrometeorites. And fun fact, 60 tons of meteorite material falls to the Earth every single day. So the Earth is gaining weight at a rate of 60 tons every day because of the fact that we're being bombarded by these micrometeorites. Most of them turn into most of these basically get burnt up into the atmosphere, creating those micrometeorite dust that falls. Very much like asteroids, you have those distinctions between the rocky meteorites and uh, iron meteorites. Now, if you find a rock, you might ask yourself, or someone might ask, how do you know that came from out of space? Well, two ways, or two basic ways. Is is the composition of that rock markedly different from the composition of all of the rock around it? If it is, that's an indication or a piece of evidence to suggest that that rock is in fact a meteorite. If it has, particularly if it has a composition of the ratio of material is of a certain variety, then again, we see that meteorites tend to have the similar sorts of composition among stonies. So if it matches that of stonies, again, that's a piece of evidence to suggest otherwise. If it has chondrules, like the one on the left, almost definitely it is a meteorite. While I believe this can happen from geologic processes, we almost invariably see this from objects that were created in the early part of the solar system. Now, irons. How do you tell whether or not a chunk of iron is from the Earth or from outer space? Well, the way to do that is to polish it. Basically, you cut it in half, presumably using a laser or diamond cutter. You cut it in half and you polish the side of it. If it's from the Earth, then it's pretty much just going to be a shiny rock. It's just going to be a shiny piece of iron. It is from outer space, however, it's going to have this pattern, which I can never remember. Starts with a W. It's very German. This pattern of feature, these sort of linear features that go through it. Those features are only caused when that piece of iron is undergoing an environment of very high pressure and temperature, the type of environment you would expect to find in the Earth's atmosphere as it's traveling at a very high rate of speed, coming down and hitting the Earth. So this is almost a dead giveaway that this is in fact coming from outer space. The other way to the other way to determine is that iron meteorites are mostly found in Antarctica because of contrast. Most of Antarctica is made of ice. It's pretty much gray and white. But if you walk around, you may be lucky enough to find a large black rock that's just that's just hanging out with nothing else around it. Chances are that is an iron meteorite. And actually, I believe you can still, there are tours where you can sign up and actually go to certain parts of Antarctica and pick and search for meteorites, um, which is on my bucket list. It's low on my bucket list, but that's definitely something I would like to see or like to do at some point. Trans-Newtonian objects. These are here the nomenclature gets messy. Trans-Newtonian objects are objects that are thought to be roughly spherical in shape. Their characteristics, from my understanding, are not very well known. They are primarily rockier materials rather than cometary materials. And they are objects beyond the orbit of Neptune, as the name would imply. If they are within the Kuiper belt, they're known as Kuiper belt objects or KBOs. If they have higher inclinations, then they're known as scattered disk objects or CDOs. Again, because of the nature of them, they're not much is known about them because, again, they are very small, they are far away, and so it is very hard to study them in any kind of detail. Now, I'm going to end today's lecture talking about dwarf planets. Dwarf planets are objects, because of the definition, a dwarf planet is a spherical object that orbits the sun that has not cleared its orbital path. There are, at the moment, around a dozen, I think, confirmed dwarf planets within the solar system. Hypothetically, we expect dozens more to be found. These trans-Newtonian objects are more than likely dwarf planets, but we haven't confirmed them as such. This image is obviously of Pluto. It was taken fairly recently by the New Horizons telescope, and it is awesome. Pluto is my favorite planet, and one of the reasons is because of this. Again, mostly, obviously, we know that Pluto is beyond the orbit of Neptune. Almost all of the other dwarf planets are beyond the orbit of Neptune, except for one, and that is Ceres. Ceres previously was characterized as an asteroid, and it was the largest of the asteroids. But because of this new definition, it has been upgraded, as it were, from asteroid to dwarf planet, because it is roughly spherical under its own mass. The thing that I love about Pluto is, oh, that's a picture of Ceres. Looks kind of like the moon. It looks kind of like Mercury, just a dead rock, spherical rock in space. with the wider regions are probably ice, regions of icy material. This may be what other the trans-Newtonian objects look like, or not, because what I love about Pluto is that prior to New Horizons, many people thought that Pluto would look something like this, but just icier, something like a rock with a whole bunch of patchy ice all over it. In fact, it has fairly complicated geology. The terrain on Pluto is quite varied for an object. If you compare it to any of the moons of Jupiter, there's really nothing that has such a complex range of topography as Pluto. I mean, you have smooth regions that are basically, we call them regio. You see them on Mars quite a bit. You also have round mountain ranges. Uh, you have cracks in them. In a way, it's more similar to the Earth's moon than Ceres is. But again, it is far more complex. No one was expecting this. Nobody was expecting Pluto to be this interesting in terms of its topography and its geology. So just goes to show we don't know until we get the data, until we get evidence. We can hypothesize all we want to, but until we get the evidence, we don't really know. And so this is Pluto is an example of that sort of axiom in that um, while if the models, if the theories are telling us one thing, then we go with it but we cannot be absolutely certain, or we cannot really put a lot of weight behind it until we get direct evidence to support it. All right. Next time I will talk about actually the formation of planetary systems and how the data that we just talked about, or how the characteristics we just talked about, inform how that formation process must have gone.